very good morning. Welcome you all to this NPTEL course on electrical distribution system analysis. Today, we are going to talk about Scada-based VVC, that is volt var control, and integrated volt var control. Let us focus on Scada-based volt var control. Scada system play pivotal role in modern power system, allowing for efficient and remote monitoring and control of electrical network components. In case of volt var control, SCADA's real-time data acquisition and control capabilities are crucial for managing devices like capacitor banks, transformers, and voltage regulators. The setup facilities the dynamic adjustment of voltage and reactive power level based on current grid conditions, leading to improved system reliability and efficiency. The control logic in these systems is often based on a set of predetermined rules, that is, when to switch on, how many layers need to be switched on, and when need to be switched off. These rules are developed from historical operation data, simulations, and studies of the distribution network. Such a rule-based approach ensures that the control actions are both consistent and based on proven strategies enhancing system stability. Now, when you talk about VAR dispatch systems, which targets reactive power management by controlling capacitor banks, it adjusts the reactive power in the system, thus improving the power factor and reduces distribution losses. Similarly, in case of voltage control system, which focuses on maintaining the voltage within specified limit, the OLTC and SVRs are crucial in adjusting transformer tap settings to respond to fluctuating load conditions, ensuring voltage levels remain within acceptable boundaries or limits. Now, there are few lack of integration between VAR and voltage control may lead to certain challenges. This independence can sometimes lead to inefficiencies or suboptimal control, as the actions on one system may not be aligned with the other one. Integration could potentially lead to a more coordinated approach, enhancing overall system performances, especially in complex networks with high renewable energy penetration. Now, let us understand what are the major components of a SCADA-based system. Substation remote terminal units, popularly known as RTUs, VBO CBR processors, switched capacitor banks with local measurement facilities, voltage regulators, LTCs, with local measurement facilities, communication infrastructure, and end-of-line voltage feedback. Now, the core component of SCADA-based systems, each component play a critical role. For instance, RTUs collect vital data from the field, while processors use the data to make informed decisions about control actions. Communication infrastructure is key for the timely and reliable transmission of control signals and operational data. End-of-line voltage feedback is essential for maintaining voltage profiles within desirable limits, especially in long rural feeders. Now, the RTU's role in monitoring key electrical parameters at strategic points provides the data backbone for the entire control processes. Decision-making algorithms within processors analyze this data, deciding when and how to adjust capacitor banks or transformer tap settings. This closed-loop control is essential for dynamic system response, adapting to changing load and generation conditions. Now, let us focus on a complete arrangement of a SCADA-based volt var control. So, we will begin with a distribution feeder. You could see that the substation transformer Where do we have OLTC? Then we can have a PT and CT. Real power and reactive power do flow in this distribution line. This is my distribution feeder. And finally, towards the load end, we do have actually capacitor banks and capacitor switches. This is my end of the feeder. So, OLTC controller provide input to my OLTC, and substation RTU capture the data and process to a upper level through a rule based mechanism, so called voltage control processor or VAR dispatch processor. Further, at distance point, my terminals of my distribution feeder do communicate through AMR or capacitor bank controller to the same rule based processor through communication interface or radio interface. So, indirectly, the decision being taken either to switch on the capacitor banks or the transformer taps based on the input received from OLTC, feeders data, capacitor bank data and AMR or voltmeters. Now, once all the data is being received by a Scada-based system and appropriate action being taken for volt-var control. Now, what are the advantages of Scada-based volt-var control over a very conventional or a traditional approach? Now, the Scada-based approach offers significant improvement over traditional manually controlled systems. Real-time monitoring and automated control reduce the need for on-site inspections and manual adjustment. Enhanced visibility and control over the network facilities, better demand response, energy conservation and overall operational efficiency. Now, still there are a bit of challenges even with this modern technology. Adapting to rapidly changing grid conditions like those caused by high level of renewable energy integration can be extremely challenging. The lack of device coordination might lead to counterproductive control actions, reducing the potential benefit of volt-var optimization. Scalability and deployment complexity are also significant concerns, particularly in terms of the need of comprehensive communication network and cyber security measures. Now, let us move to integrated volt-var control. Now, integrated volt-var control, acronyms such as IVVC, is an advanced approach in volt-var control, integrating multiple control devices to optimize operational performances. It aims to determine the most effective control actions for all devices, voltage regulating and VAR control devices in a system. IVVC, that is integrated volt-var control, objective extend beyond traditional power quality measures to include efficiency, reliability and cost effectiveness. Goals include minimizing line losses, maintaining voltage within specified limit and maximizing the efficiency of power distribution. Unlike simpler system, IVVC does not just react to changes, but proactively seek the best operational states, uses advanced algorithms to determine optimal setting for each device in response to real-time grid conditions. The goal is to achieve operational objective set by the utility without violating any operating constraints. It involves a synergy between optimization technique and technological development for improved distribution network operations. VVC requires real-time monitoring data and control of both substation and feeder devices. Centralized control gathers data from meters and runs volt-var optimization algorithm, which are then communicated to the field devices through the Scada system. Scada plays a crucial role in the integration of all IVVC components. Distribution Management System DMS supports centralized control and is essential for what is often referred to as DMS-based volt-var control. Advanced metering infrastructure, that is AMI, which includes meters, communication networks, and data management systems. It ensures real-time observability at customer service points, crucial for effective volt war control. MDMS, that is Meter Data Management System, manages and analyzes meter data, converting it into actionable insights for the utility. Now, IVVC continuously updates its network model to reflect real-time conditions, including load changes and distributed generation impacts. The dynamic modeling is crucial for accurate decision making and responsive control actions. Intelligent electronic devices serve as smart meters and supervisory controllers, relaying information and executing control commands. They monitor and manage key aspects like voltage, capacitor banks, tap changes in voltage regulators, and load measurements. The substation remote terminal unit acts as a data hub, aggregating information from all substation IEDs. While centralized in control, IVVC leverages distributed intelligence offered by IEDs and RTUs across the network. The combination allows for both broad oversight and localized decision making, catering to specific needs of different network segments. Now, further, geographic information system, that is GIS integration, is used to create a geographically aware model of the network, enhancing the understanding of physical locations and their impact on electrical parameters. Helps in visualizing and managing the special aspects of the distribution networks. Accurate electrical modeling is essential for IVVC. Up-to-date electrical model of the distribution network can be carried out through this process. This model integrates GIS data and real-time updates via Scada, encompassing both permanent and temporary network changes. Now, one of the important aspects, online power flow analysis, that is OLPF, tools analyze current network conditions, predict outcomes of different control actions, and support decision making. Helps in assessing the impact of different control strategies before they are implemented. IVVC systems are often tailored to specific utility needs, allowing for custom strategic that align with unique operational goals and constraints. This includes consideration like local regulations, specific grid configurations, and customer demographics. Now, if you focus on the arrangements of integrated volt var control, we can see that actually geographic information system through distribution system model and input from actually manual configuration can be merged at my distribution system model. Further, the inputs may be given to my OLPF after receiving inputs through IVVC optimizing engine. Now, all this input to the Scada system being received by my IVVC, and further information can be injected to my distribution system model. Now, moving to the substation side, we will have actually OLTC and substation capacitor banks. Through IEDs, actually we can enter as an input to my substation RTUs. Further, the line voltage regulator, switched capacitor banks, all the inputs can get into my Scada system. From the field, I can also get the data from AMI through MDMS along with the line conditions or switching strategies. So, probably we can see it is slightly a different arrangement compared to Scada-based volt var control. It is Scada-based along with further field data which has been captured through GIS. So, if you see majorly this component which is slightly unique compared to my Scada-based volt var controls. Now, How do we coordinate across multiple objectives? Balances various objectives such as improving power factor, reducing losses, maintaining voltage levels, and ensuring equipment longevity. It offers the flexibility to prioritize different goals as operational conditions or utility strategic changes. Now, there are a bit of challenges due to high DR penetration. As DRs increases, managing reverse power flow and maintaining grid stability become more and more complex. IVVC is equipped to handle the challenges, making it particularly relevant in modern grids with high renewable energy integration. Now, cost is an important issue because the implementation and maintenance of IVVC can be resource intensive due to the need for advanced technologies and robust communication networks. However, the long-term operational savings and efficiency gains can offset initial investment costs. Future enhancements in IVVC may include greater automation, use of artificial intelligence for predictive analysis, and deeper integration with renewable energy sources. As the energy sector evolves, IVVC is expected to incorporate more advanced features to maintain its effectiveness and efficiency. So, with this we come to a conclusion of Scada-based and integrated based volt var control. Thank you.